Welcome back to the Deep Dive. Today we are taking on a topic that impacts your life every single day, literally every meal. We're doing a systematic deep dive into foodborne microorganisms.
And our goal here is to move beyond just, the vague warnings. We want to give you the scientific framework. We've gone through the sources to show you the difference between a bug that causes, say, mild diarrhea and one that can cause immediate life-threatening paralysis.
We've pulled together clinical studies, public health data, all of it, and we're distilling the most critical information. The infection pathways, the sources, the real risks. And just to be clear, this is all for informational context. It is absolutely not a substitute for medical advice.
Right. And to really get a handle on this, we have to start with 3 foundational concepts. Understanding these really changes how you look at risk in your own kitchen.
Okay, let's start with the big one. The difference between an infection and an intoxication. They sound similar, but their effects are, well, wildly different.
Yes. And what's fascinating here is the timing and the mechanism. So a foodborne infection is when you actually consume the living microorganism.
The bacteria, virus.
Exactly, the bacteria, virus, or parasite. And it has to multiply inside your gut before you get sick. It takes time, usually 12 to 72 hours, for it to build up enough numbers to cause symptoms.
So classic examples would be Salmonella or Campylobacter.
That's right. In an infection, the microbe is the weapon, and it needs time to deploy.
But with a foodborne intoxication, it's much, much faster, isn't it?
It is. With intoxication, you are consuming the microbe's preformed poison, the toxin itself.
Right.
The bacteria that made it could even be, killed off by cooking.
But the chemical poison is still there in the food.
Precisely. And it instantly attacks your system.
So if food is contaminated and then just sits out, the organism might die off, but the toxin it created can still make you critically ill.
That's exactly right. And that's why intoxication symptoms are often so rapid, we're talking within hours, and can be much more severe. The most notorious one is the toxin from Clostridium botulinum.
Okay, that distinction alone is huge. So what's the last foundational concept? I saw zoonosis mentioned everywhere in the sources.
Zoonosis is central to all of this. It just means a disease transmitted from an animal to a human. The vast majority of the bacteria we worry about, like E. coli, Campylobacter, Salmonella, they're all zoonotic.
Meaning the source isn't just a dirty kitchen, it starts back at the farm animal.
Right. The microbes live naturally in the gut of poultry or cattle. The risk comes in during processing or when animal waste gets into the water or onto the fields.
That sets the stage perfectly. So let's dive into section 1. The bacterial heavy hitters. These are the ones tied to the animal food chain.
And we have to begin with Salmonella enterica. It's almost, ubiquitous in the environment.
And the sources are the ones we always hear about. Raw eggs, undercooked chicken.
Raw eggs, poultry, yes. But also raw milk and even produce that's been contaminated by, say, runoff water from a field.
Now, when people get salmonellosis, we think of gastroenteritis fever, pain. For a healthy person, it's awful, but it passes. Where's the real risk?
The real risk, the key detail, is sepsis. Salmonella has a medium to high risk of what we call translocation.
Meaning it gets out of the gut.
It spreads from the gut right into the bloodstream. That's sepsis. And it is a life-threatening emergency. It disproportionately affects infants, the elderly, and anyone who's immunocompromised.
That's the difference between a few bad days and a true medical crisis. All right, next up, the classic raw chicken danger, Campylobacter.
Right, specifically C. jejuni and C. coli. Uncooked chicken and unpasteurized milk are the main culprits here. It's one of the most common causes of bacterial diarrhea. And again, it's usually self-limiting, but there's this rare and critical complication.
Guillain-Barré syndrome, GBS. I've heard the term, but what's actually happening? How does a gut infection cause a nervous system disorder?
It's a case of biological mistaken identity. Scientists call it molecular mimicry. The surface of the Campylobacter bacterium looks incredibly similar to parts of our own nerve cells.
So the body's trying to fight the infection.
Right. It makes antibodies to fight the Campylobacter. But after the infection is gone, those same antibodies can mistakenly attack your nerves.
Leading to paralysis.
Yes. Temporary, sometimes prolonged paralysis. And that devastating link is what elevates the risk of Campylobacter beyond just standard food poisoning.
That is where this gets truly terrifying. Okay, now for the one that causes so much fear, especially for parents, E. coli, the hamburger bug.
Specifically, the Shiga toxin-producing strains, or STEC, like O157.H7. This is a high-risk pathogen because of the powerful toxin it makes.
And sources are undercooked ground meat.
Undercooked ground meat, right, where contamination gets mixed all the way through. Also, raw milk and produce that's been contaminated by cattle feces. It causes severe, often bloody diarrhea.
But the danger isn't just the diarrhea, it's what happens next, particularly in children.
Absolutely. The key takeaway is this isn't just a digestive disease. The Shiga toxin gets absorbed from the gut, travels through the bloodstream, and attacks the lining of blood vessels.
Especially in the kidneys.
Especially in the kidneys. And that leads to hemolytic uremic syndrome, or HUS.
HUS. So that involves kidney failure and the destruction of red blood cells. That sounds like a vascular emergency.
It is. Once HUS develops, it's intensive care, dialysis. It can be fatal. It's all because of that one specific toxin.
Now we have two unique bacteria that sort of break the mold. First, the cold-tolerant one, Listeria monocytogenes.
Listeria is tricky. It challenges one of our basic food safety rules. Most pathogens slow down in the fridge, but Listeria can actually multiply at refrigerator temperatures.
So putting something in the fridge isn't a kill step. It's just a pause button. But for Listeria, the pause is less effective. Where do we find it?
It's often in ready-to-eat foods that don't get reheated. Things like soft cheeses from raw milk, deli meats, smoked fish. For a healthy person, it might just feel like a mild flu.
But the extreme risk here is for specific groups.
The risk for pregnant women is incredibly high. If they get listeriosis, it can cross the placenta, it can cause miscarriage, stillbirth, or a life-threatening infection in the newborn. And in the elderly or immunocompromised, it can rapidly cause meningitis or sepsis. This is why those warnings are so specific during pregnancy.
And finally, the ultimate danger in the intoxication world. Clostridium botulinum. This is just pure poison in a jar.
Yes, and what's crucial to understand is the source. C. botulinum is anaerobic. It thrives where there's no oxygen.
Which is why the danger is always with things like home canning.
Improperly sterilized home preserves, exactly. Especially low-acid things like vegetables or meat that are canned or vacuum-packed.
And the mechanism is just terrifyingly fast.
It produces the botulinum neurotoxin, which is one of the most potent biological toxins known. It enters the bloodstream and blocks the signals from your nerves to your muscles.
It just stops the nerves from telling the muscles what to do.
Precisely, leading to descending paralysis. It starts with double vision, difficulty swallowing, and can end in fatal respiratory failure because the diaphragm stops moving. It requires emergency antitoxin treatment.
And the sources mention one other key detail.
Right. Never, ever give honey to an infant under 1 year old. Their gut isn't developed enough to stop C. botulinum spores from growing and producing the toxin right inside their body.
That overview really shows how knowing the mechanism, infection, toxin, cold tolerance is the key. So now let's pivot to contamination that isn't primarily about animal protein. Let's talk produce, parasites, and viruses.
Right, because plants don't produce these pathogens themselves. They're just passive vectors. So the question is, how does my lettuce get E. coli?
You have to look at the contamination pathways out in the field.
Exactly. The sources are clear. Bacteria like E. coli, Salmonella, they get onto vegetables from contaminated irrigation water, from animal feces in the fields, or just poor hygiene during harvesting.
And the risk for produce is so high because we often eat it raw. We take away our main defense.
We take away the thermal kill step. There's no cooking to destroy the pathogens on lettuce or sprouts or spinach. This is why thorough washing is so essential. It's the only chance you get to physically remove the microbes.
Okay, let's move to the viral threats. These are famous for causing these huge, rapid, and very unpleasant outbreaks.
And the primary culprit there is norovirus. It is the definition of contagious. It spreads so easily from person to person or from food handled by an infected person. Salads, sandwiches, raw shellfish.
The famous cruise ship villain.
It is. It causes that really rapid onset vomiting and diarrhea, and it just rips through closed environments like schools or ships because the infectious dose is so low, it only takes a few viral particles to make you sick.
And the other major viral threat is different. It targets a whole other organ, hepatitis A.
Hepatitis A virus, or HAV, comes from fecally contaminated water. So raw produce washed in that water or raw shellfish from that water. It causes acute liver inflammation.
How is that different from norovirus?
Well, norovirus is a very short, intense gut illness. HAV has a much slower incubation, and it goes for the liver. You see symptoms like jaundice, intense fatigue, dark urine. Most people recover, but there's a risk of severe, even life-threatening liver failure.
And finally, there are the parasitic protozoans, names like Giardia, Cryptosporidium. The danger here seems to be more about how long they last.
That's the critical distinction. Their source is almost always contaminated water. Once you ingest them, they set up shop in your gut lining. They're not usually fatal in healthy people, but they cause a prolonged, persistent illness.
Prolonged, as in weeks or months.
Oh, yes. Chronic watery diarrhea, abdominal pain, and often significant weight loss because your body just can't absorb nutrients. The risk is that the symptoms just go on, far longer than a typical bacterial infection.
Okay, we've covered the whole spectrum. Fast-acting toxins, slow zoonotic infections, the cold-tolerant metas, waterborne viruses. Before we talk prevention, let's try to synthesize this into a clear risk stratification.
We can definitely categorize the risk based on the potential for, say, hospitalization or long-term harm.
Let's start with low to medium risk, the ones that are awful, but usually self-limiting.
That would mainly be mild cases of Staph aureus intoxication that resolves pretty quickly, and uncomplicated cases of Campylobacter or Salmonella in a healthy young adult. You'll feel terrible, but you'll almost certainly recover on your own.
And then medium to high risk, where you might need medical intervention.
This is where we put E. coli 0157.H7 because of that potential for HUS. Also, Listeria monocytogenes in those high-risk groups, and serious cases of Hepatitis A or a Salmonella infection that's spreading and needs antibiotics.
And finally, the very high life-threatening risks, the true medical emergencies.
Top of that list is Clostridium botulinum. The paralysis requires immediate antitoxin. Also, Listeria that's caused meningitis or sepsis, and a fully developed case of HUS from EHUC. We also have to include Vibrio vulnificus sepsis. It's rare, but it's an incredibly deadly infection from raw seafood, especially for people with liver disease.
Understanding that stratification is so important. Okay, let's tie this all together. We know the why now. So what does this mean for our daily habits? Let's go through the core rules of protection and connect them to the microbes we've discussed.
These rules come directly from the transmission pathways we just talked about.
Rule 1, cleanliness. How does just washing your hands defeat some of these bugs?
Well, it stops the person-to-person spread of viruses like Norovirus, but crucially, it also prevents cross-contamination. A knife or cutting board that touched raw chicken can instantly transfer Salmonella or Campylobacter to your salad. So cleanliness is all about breaking that transfer.
Rule 2, separate raw and cooked. This is the practical defense against that zoonotic reservoir.
Exactly. You keep raw meat and poultry away from everything else so the juices, which might contain Campylobacter, don't drip onto your lettuce. One cutting board for raw meat, another for produce. It's your primary defense against those animal-sourced bacteria.
Rule 3, adequate cooking. Our definitive kill step. What's the magic number?
At least 70 degrees Celsius, that's about 160 Fahrenheit, internal temperature for ground meats and poultry. That heat destroys bacteria like Salmonella and E. coli, 0157H7. And eggs have to be cooked until the yolk is firm. No liquid.
Rule 4, safe storage. This is how we fight the timer-based risks.
You have to get cooked food into the fridge within 1 to 2 hours. You're minimizing the time it spends in the danger zone, between about 4 and 60 degrees Celsius, where pathogens grow fastest. And quick refrigeration stops Staphylococcus aureus from producing its heat-staple toxin.
Rule 5, reliable water and milk. This is the defense against environmental contamination.
Always use pasteurized milk. That's a kill step for Campylobacter and Brucella. And if your water is questionable, boiling is the only reliable way to kill protozoan cysts like Giardia and viruses like Hepatitis A.
And finally, Rule 6, extra caution for the high-risk groups.
For them, this isn't optional. Pregnant individuals, infants, the elderly, they must strictly avoid raw or undercooked meats, raw eggs, and those specific risk foods we talked about. Raw milk, soft cheeses, raw sprouts. For them, it's a necessary shield against sepsis, HUS, and meningitis.
This deep dive has really shown you the scientific why behind all those warnings. You now know that when you separate a cutting board, you're not just following a rule, you're breaking the transmission chain for Campylobacter.
And when you cool leftovers quickly, you are specifically preventing toxin production. The goal was to give you that systematic framework so you can analyze any future food safety news by asking, is it an intoxication or an infection? Is the risk zoonotic or environmental?
And here's a final provocative thought for you to chew on. Now that you understand that the biggest risk difference is often whether a microbe produces a toxin, think about public health policy. Should the focus be on destroying the bacterium in the food chain? Or should it be on preventing the conditions, like improper storage, that allow the deadliest toxins to be produced in the first place?
Focusing on preventing the environment that breeds toxins, like better home canning education or enforcing faster refrigeration in supply chains, might save more lives than just focusing on the animal. Think about where the most effective leverage point truly is.
Until next time, keep learning and keep asking why.